Okay, good. So thanks so much for having me and for giving me this opportunity to tell you a little bit about something that I've become very interested in over the last few months. So this really came about because I realized that I know hardly anything about 4D de Sitter, and I figured it's about time. So, but it's work in progress. So this is very exciting for me, but this is also, so please, like, if you have any input, any questions, I'm happy to hear. Yes, good. So, but I think the main motivation for me also was just this fact that I think we have a really desperate need to get a microscopic model for de Sitter quantum gravity. After all, it describes our universe. However, I think the question that we should all ask ourselves is like, how can we constrain such a microscopic model if all that we have is like low energy macroscopic data? And I think at least like a calculable observable that I like very much is the sphere partition function, because it's a gauge invariant quantity and it's systematically calculable. And whatever microscopic model someone will bring up, the macroscopic data that we get from the sphere partition function has to match. Moreover, according to this conjecture of Gibbons and Hawking, the sphere partition function encodes the entropy of de Sitter. So we have this cosmological event horizon that's surrounding us, and conjecturally an entropy is encoded in this horizon. However, we still have like all these open puzzles, all these open questions, because what is this de Sitter entropy? Is it counting anything? Are we expecting microstates? Are we expecting this is an entanglement entropy? What are we expecting? And moreover, and we will hear talks about this in this workshop, we have the conformal mode problem that famously now leaves us with an imaginary problem. So how do we really like get about this? So in the last few years, I think very successfully, what we did is that we went to lower space-time dimensions. So we went to 2 and 3D de Sitter. And because we realized it's a really tractable and calculable observables, laboratories. And we've been like, with the motivation, of course, that in the end, whatever we're gaining in these low D models, we're going to export back to 4D de Sitter, because after all, we want to study our real world. So, I mean, a lot of progress has been made and in like 2D de Sitter, and like I think that the complex lower string that we developed like beginning of the year gave us a framework, a matrix model framework to study the sphere partition function from a completely different angle. But still, where are we standing in terms of 4D de Sitter? So what model of 4D de Sitter do we have? This is our world. So what I want to do in this talk a little bit is like give you a little bit of like the status report of what I've learned over the last few months about the status of 4D de Sitter. And maybe, I mean, at least definitely in the absence of time-like boundaries, the model of 4D de Sitter that I think is still the maybe only one that we have, which is in the spirit of DSCFT, which relates the late time wave function of 4D de Sitter to a boundary CFT3. And this boundary CFT3 is given in terms of a Lagrangian, which is an SPN vector model. So I'll tell you a little bit about this status. But then this wave function story here, this DSCFT story here is very Lorentzian. So we've learned that a lot of data is encoded in Euclidean signature. So then we want to pose the question, what is the microscopic completion of this 4D de Sitter with positive, so this 4D higher spin model with positive cosmological constant on this sphere? So what data, what does it encode? And we will show you that there's a bunch of puzzles that we will run into, and then I'll still go back to my 2D laboratories to explore like a 2D model, and we will see that some lessons we can learn here and also some obstacles that we can come up in this 2D model for these 4D higher spin theories. So the roadmap is the following. So we will start over here. This is going to be 2 slides in which I'm going to be a bit technical, but we need to kind of fuel up, we need to get started. So I'll tell you a little bit about group characters of the de Sitter symmetry group. I'll then tell you just like, what's the status of this, to some extent at least, of this 4D higher spin theories in DS4 from this like wave function perspective. I'll tell you a little bit like what happens if we start putting this theory on the 4th sphere. So what happens if we start to understand the microscopic completion of this higher spin theory on the 4th sphere. I'll then tell you about this 2D toy model that captures some aspects of higher spin theories, but to really bring this story home, I'll introduce what I'll call Timelike Toda theory, which is a model for 2D higher spins. So let's get started. So the de Sitter symmetry group is SO1D+1, which is a non-compact group. So what do you want to know about the group? Among many other things are the group characters. Because it's non-compact, you have to work a little harder. But still, the Chandra worked out the characters for the unitary irreducible representations of this SO1D+1 asymmetry group of the Lorentzian de Sitter. And in general, you have a representation R. Here, we're going to restrict it to the subgroup SO11. So we're going to restrict it to the subgroup that's generating time translation. So it's kind of moving the global patch like this. In particular, in one of the static patches, it's really like a flow that goes in one direction. So it's basically like the Hamiltonian in the static patch. But of course, it's a non-compact group, so the eigenvalues are continuous. And indeed, we can write, for example, for the principal series, which is encoding particles that are very heavy. So for principal series particles, for example, something with spin S and some conformal dimension 3/2 in ds4. So the 3 is because I'm in 3 space dimensions. So the Chandra character for these massive particles with spin S takes the following form. So indeed, this is the group element that's generating time translations in the static patch. And here I have this trace. And then the group character is given by this following expression over here. Again, these threes, all these threes are because I'm in the specific 3 space dimensions. They would be changed if I'm in any other dimension. And I can also write this character in terms of this integral over here with some distribution rho that you can find in this paper over here. And I'm integrating over omega, which are really the eigenvalues of this H. So now this is a very Lorentzian concept. These are the group characters, this is the conformal dimension, this is spin. So I want to talk about the sphere. So a priori, there's no reason whatsoever that the sphere would know anything about this. Why would the sphere know about something like this? However, in this work by these 4 gentlemen over here, and I think Albert and Seymour are both here, so back them with questions. So in this really nice work here, these authors initiated a program showing that the sphere partition function, so the Euclidean sphere partition function. And the sphere partition function is important also because Wick rotating global and static de Sitter to Euclidean signature gives you the sphere. So Wick rotating this, looking at the sphere partition function of this theory, it can be expressed in terms of unitary Lorentzian characters. So you have a Euclidean thing, and it captures Lorentzian data. So there's really data in the sphere partition function. So for example, if you look at, again, a massive scalar on the 4th sphere, I take it spinless, and you evaluate this determinant over here to leading order, this determinant in a heat kernel analysis, then what you find is the following expression. Ignore this first part for now, it's just some kinematical term, but remember this term over here. This term was nothing else than the Chandra character of this particle, but it's a Euclidean sphere partition function. So it still knows about the conformal dimension and the spin. So this is all the mathematics that I wanted to convey here, just knowing that sphere partition function captures Lorentzian data. So because now we can get started. So now we can get started and look at 4D higher spin theories. And so I don't have, for the sake of time, I don't have so much time, but please bug me with more questions. In this slide, I just wanted to summarize roughly what's the status. So is that, for example, minimal higher spin theory. So minimal just means that I have only even spins. So this minimal higher spin theory in de Sitter is dual to an SPN vector model living at the boundary. More in formulas, we have this late time higher spin wave function. So this is some Hartle-Hawking, Bunch-Davies wave function that depends on some higher spin fields. So this is a scalar and then a bunch of higher spin fields here. And this is dual to the CFT partition function of an SPN vector model. So these chi's here are n anti-commuting real scalars. So, and all these B's here, they're basically the sources for the conserved currents. So the conserved currents on the side, which are just expressions in terms of the chi. So let's take the group theory into game. So this B here is a scalar, and it transforms in a complementary series of SO14, so the DS4 symmetry group. And then we have all these higher spin fields, they're Frontstel fields, and this is a really takeaway message that I want you to remember. These Frontstel fields are transforming the discrete series representation of SO14. And the discrete series representation I'm labeling by this capital D, with the subscript being S, the spin, And then the second subscript is called the depth, because this discrete series fields, these Fresnel fields, they're really partially massless fields. So they're living here. So in de Sitter, you have like the Iguchi bound. The Iguchi bound is more or less the unitarity bound. And in general, everything that lives below the Iguchi bound is non-unitary. However, at very special points, and I'm indicating those by these numbers here, there's enough gauge redundancy that develops to kill all the ghostly degrees of freedom. This comes at a cost. It comes at the cost of reducing the number of degrees of freedom. And so all these Fresnel fields, or those fields that are living down here, they have 2 degrees of freedom, which I'm indicating by this plus minus superscript over here, which is roughly like helicity. So, but the takeaway message is that we have this like discrete series representation in which these like higher spin fields are living in SO1 form. So this is really like the status quo more or less of this 4D higher spin theory, and the rest of my knowledge, this is where we are in 4D. So now the question that we might want to ask us, so we have one model of 4D de Sitter. So what is this model of 4D de Sitter that we have on this sphere? What is the microscopic completion of this 4D model on the 4th sphere? We're running into trouble right away, and there's no Lagrangian for this bulk higher spin theory. So what do we do if we have no Lagrangian? So what we can still do, even in the absence of a Lagrangian, is that, as I've hopefully conveyed in the previous slide, we know the conformal dimension and the spin of all these higher spin fields. So we can still write down a one-loop determinant calculation, a one-loop determinant for the partition function. And so for the one loop, what we need to do is we need to take the characters of all these higher spin fields and this scalar, and we need to sum them up. And that's what we're doing here. So this is the sum of all the even spins, just because I'm doing minimal higher spin theory. And then something very, very miraculous happens. So you take this infinite power of higher spin tails, you take these 4D characters of this 4D higher spin bulk theory, sum them all up, and then you get a 3D character. So you get the character of a field that lives on a 3-sphere. So in particular, this quantity over here encodes divergences, but these are divergences inherently tied to 3D. So how do you make sense of divergences that are living in a 3D sphere on a 4th sphere that has no boundary? So that's very interesting. I think that's an incredibly interesting puzzle that we're facing here. So what are we losing? So what do we gain here? Moreover, like this 3D character in the ADS higher spin story gave a lot of insights about the higher spin, about the dual theory. So I think there's lots of things that we can learn by studying this character here. And I have some backup slides if you want to know exactly what's popping up here. Moreover, what we have to deal with is that this is de Sitter. We are in the 4th sphere. There's no boundaries. It's not like in ADS where we put Dirichlet boundary conditions anywhere. So in de Sitter, we need to gauge by the higher spin group. So we have this extra volume of this higher spin group. So how do we make sense of this volume of this higher spin group? So I think basically what we see from this formula is that there's very promising ideas in these formulas, but we still need to understand what it is. And so this is what I want to do now. So this basically, like these very interesting features that we see, they really, as far as I'm concerned at least, they really motivate to seek computable like analogs, maybe lower dimensional, maybe higher dimensional analogs. In like ADS, you can push it to arbitrary dimension. Again, another problem of de Sitter, or like a feature of de Sitter. Let's put it a feature. So a feature of de Sitter is that you cannot sum these higher spin characters in any dimension that's higher than DS4. So if you try to sum characters in like some 5D de Sitter, nothing works. Like this is not summable. So what we can try to look at is some lower dimensional setups. So what do we have at hand in lower dimension? This is like 2D de Sitter, this is 3D de Sitter. So I like 3D de Sitter, it's deeply at my heart. But what I want to talk about today is like 2D de Sitter. And the reason why I want to talk about 2D de Sitter is because we can really couple matter to this theory. And moreover, there's this table over here. So, and what I hope I'm said many times before is that we had this discrete series representation in the SO14 asymmetry group. So the discrete series, which is like basically the gauge fields. So principal or massive fields, complementary light fields, discrete is gauge fields. And the discrete series representation is absent in DS3. So I cannot study like this discrete series representation in DS3. However, and also just like I want to make sure that like we are also all on the same page. Still, what am I talking about higher spins? I mean, this is 2D. Like spin in 4D was associated to the SO3 rotation group. So this is 2D, like the spin would be associated to the SO1, which is just some grading. But still, the message that I want to the idea that I want to pursue here is that given that we still have a discrete series representation in SO1, 2, the models that we can find, maybe they still capture enough ingredients and enough similarities to the 4D theory to maybe overcome and maybe understand what is this dimensional reduced character, what is the meaning of it, what is the dual theory. So that's why I want to discuss 2D coupled to matter. And the first model in which, the first time model that we are going to discuss, which is a model that captures discrete series representation, is what's called Timelike Liouville theory. So Timelike Liouville theory, you can think of as the following, in terms of the following path integral. So say you start out with some 2D gravity theory on the sphere, you couple it to matter, you already integrate out all the matter fields, and then you go to Weyl gauge on the sphere. So in 2 dimensions, the metric Gij has these 3 degrees of freedom, you kill 2 with the diffeos, and what's left over is the 1 field phi, which is the Weyl factor, which captures all the degrees of freedom. And then this theory conjecturally goes to this setup over here. So this 2 over here is the Euler characteristic because I'm on a sphere. Theta is just some coupling to the Euler characteristic. This Cm is my matter theory, which I'm assuming to be a 2-dimensional CFT. I have some BC ghost system that comes because I'm going to Weyl gauge. So, but it captures in terms of this conformal anomaly on the sphere. And then what's left over, what really captures the fluctuating degrees of freedom, like the Weyl factor, is this expression over here, where in the exponent over here, this is Timelike Liouville theory. So this is the Timelike Liouville action. And I have it here, but let's also discuss this final ingredient here. So even after going to Weyl gauge, I still have residual symmetries on the sphere, and this residual symmetries are the Möbius transformations. That's why I'm dividing my PSL2C. So that's this thing here. So now I want to put this Timelike Liouville theory on a fiducial 2-sphere metric. So I'm taking this G tilde over here to be a background S2 metric. So the Fubini's 2D metric or whatever round metric on a sphere that you so want. And then this Timelike Liouville action takes the following form. What I want to stress here is that, and if you have encountered Liouville theory before, you have most likely not encountered Timelike Liouville theory, because Timelike Liouville theory differs from space-like in these 2 signs here. So you have a negative sign for the kinetic term, and you have a negative sign for this linear term over here. And Timelike Liouville theory is also a 2-dimensional CFT, and as such, it has a central charge, which is given by this following expression over here, where this little q over here is related to this beta over here in the following way, in essentially such a way to make this a 2-dimensional CFT. Now, I don't want anything to depend on my gauge choice, so I'm imposing vanishing conformal anomaly, which is this constraint over here. And let me just stress that this b over here is the dimension of length squared. It's like the Ricci on the sphere. All tildes are background, so they are related to G tilde. Very good. So this theory, now if I couple it to matter and I take this matter central charge very, very, very large, then this theory admits a saddle. So I have this 2D theory that has a saddle. In the limit, and the saddle is governed by this C matter, or of course, if C matter is very, very large, by this vanishing conformal anomaly condition, it implies that C Timelike Liouville theory is very, very small. So let me go back. This Timelike Liouville theory is very, very small, or equivalently from this constraint, you see that that's the limit in which beta is going to 0. So on the sphere, now this Timelike Liouville theory has a saddle. Just so we are all on the same page, I wrote down the equations of motion. So the equations of motion are this. I forget about this term because we can actually find a constant solution. So essentially, because we have this minus sign over here, this equation admits a solution, a real valued solution. And this real valued solution is just some phi star that's constant and real. And so we started out with some G tilde. There was a sphere topology. The phi is constant, so it's merely a rescaling of the size of the sphere, but we have a sphere saddle. We have a sphere geometry. So we won. We have the Euclidean de Sitter realization, which is the 2-sphere of 2D de Sitter. And if we study now fluctuations around the sphere of this path integral, we find the following expression. So we find there are various pieces in here. Let me describe them. So we have this part over here, which comes, so this L plus 1, or the eigenvalues of the spherical Laplacian on the 2 sphere. So you see, first and foremost, you see that for L is equal to 1, there's a 0 mode. And the eigenvalues for each L or 2L plus 1-fold degenerates, so this is 3-fold degenerate 0 mode. And we will use this 3-fold degenerate 0 mode to kill the 3 non-compact directions of PSL2C. So that's why this path integral actually a priori made sense, because I divided by PSL2C. So in principle, you could have told me, oh, this is just infinite or 0. But I have like 3 non-compact directions. So yeah, I have like 3 0 modes, and here I'm using these 3 0 modes to kill this infinite volume of PSL2C and make it SO3. And then I do a proper Faddeev-Popov gauge fixing, and the proper Faddeev-Popov gauge fixing tells me that this Faddeev-Popov determinant is Q-cube, with the cube being the 3 0 modes. Now, what I don't want to discuss, but I want to highlight, is that Timelike Liouville theory is a 2D model that captures the conformal mode problem, because from what you see here as well is that there are some Gaussian unsuppressed terms and some Gaussian suppressed terms, so you need to deal with big quotations. This is very interesting. I leave this discussion to other people, but please back me with it if you're interested. So, but because the message that I want to go back to where did I start out? I started out with some higher spin theories. I started out with some particles, some Frontstall fields, some higher spin fields transforming in the discrete series representation. So let me go back to I was looking for 2D setups that had discrete series. So if I do the heat kernel analysis of this determinant of nabla squared plus m squared, where m squared is -2. Also just let me say this again here to not cause confusion. So this is m squared is -2, but I'm not looking at this as a scalar that is tachyonic. This is a gauge field. So as a gauge field, it's okay if it has mass squared, it's -2. So, but then I do the heat kernel analysis and I find this expression over here. Again, kinematical term, ignore it. But this thing here in red is a discrete series character in SO1, 2. So in general, the discrete series higher tensor character takes the following form. So we recognize this as this discrete series character with delta equal to 2. So the wow factor is like the 2D graviton. And for this other stuff over here is very, very interesting and very important, and it pops up only in de Sitter. And it comes because my sum here actually omits the L equal to 1 modes. So these are this comes because of the 0 modes. In higher dimensions, people have interpreted this as an edge character that lives on a codimension 2 surface. That's a bit difficult to do in DS2 because codimension 2 is S0, which is 2 points. But the higher dimensional interpretation is this as an edge character. So good. We've one discrete series character. Actually, but if you want to map it to some higher dimensional models, we need to find more. But before I'm going to find more for you, let me also mention one more thing about Timelike Liouville theory, because it's very structured. And actually, my higher spin model is going to capture a lot of these ingredients as well, is that this theory is incredibly structured. I can calculate 2 loops, 3 loops, 4 loops if I so want to, from a path integral perspective. So, and all the UV divergences, so at 3 loop you have 25 diagrams, and they cancel very nicely that you don't have to do any UV divergences. Of course, this is 2D, so they had to cancel, but still, it's very interesting how they cancel. And what's left over is the following expression. So this is really a path integral calculation. So you have at 2 loop order, we have this little Milonic type diagram, and then at 3 loop, you have this 4 diagrams that survive, and so on and so forth. But what I want to stress also in this formula is this factor over here. So you have this 1 over here is the real saddle that I showed you on the previous slide, but we have 1 more saddle, only one and only one. We have 1 more non-perturbative saddle. And what I want to say is maybe what we should also look at is the signs in between 2 saddles. So very good. So, and fortunately, actually here in this 2D setup, we are very fortunate that we can actually use yet a different machinery to calculate the sphere partition function. And this machinery is using the conformal bootstrap. It's using the detour that Timelike Liouville theory is also a 2-dimensional CFD. So we can take the structure constants. So the C mu beta 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 is a structure constant. The beta is like the alpha, so it's because I have the area operator e to the power of 2 beta phi. So if I take this structure constant and I can relate to the sphere partition function, then I get this closed form expression for this thing here. So if I expand this for small beta, I get this. So on the nose. So I have a sphere partition function that I know to all loop order. So I can also check all the signs, all the i's, all the not i's. I can check everything. So okay, but now let's go back to where we actually wanted to head. But I hope that you have in mind that we have this toy model that captures the discrete series. Right. So let's look. And let me also stress that this is like really like a work in progress now. So any input, any questions, if you tell me this is 0, tell me. I mean, I want to know. So what I want to say is that it's like, so basically searching for models that capture more discrete series characters, I went to look at Toda. So Toda theory is a higher spin generalization of Liouville theory. And here specifically, I want to look at SLN Toda theory. So SLN Toda takes the following form. So it has a kinetic term. Also, let me stress that I'm looking at Timelike Toda. So if you have heard about Toda theory, you've most likely heard about Spacelike Toda, because Spacelike Toda is part of AGT. This is Timelike Toda, so I'm flipping signs again. So I have a negative sign for the kinetic term, which then captures the conformal mode problem, and I have a negative sign in terms of in front of the linear term. The wild factor in Timelike Liouville theory is now this bold symbol phi. This bold symbol phi is now a field in the root space of this Lie algebra SLN. So it's like a vector space, a field in a vector space. And the basis elements are like these EIs, and the EIs are nothing else than the n-1 simple roots of this Lie algebra. And the inner product gives me the Cartan matrix. So this inner product pops up here. So, and SLN Toda theory has not just a stress tensor, but it has really like n-1 holomorphic currents and its anti-holomorphic counterparts. This makes this really like a higher spin theory. And this n-1 currents, they form a Wn algebra, and the subalgebra is the Virasoro algebra, so it has still a central charge, and this central charge is given by this following expression over here. Like this n is related to this SLN here. If you take n equal to 2, not surprisingly, you get the central charge of Timelike Liouville theory. So one way that I think you can look at this theory is in the following way. So you can take some 2D higher spin theory with some bunch of 2D higher spin tails, or some G's and some H's with some indices. You take some higher spin action, which generalizes the Einstein-Hilbert action if you so want. I don't necessarily need to know this. I take some meta theory, which had some global higher spin symmetry group. I already integrate out the meta fields here. And now say I go to some sort of Weyl gauge for this theory, for this higher spin theory. So I don't only go to Weyl gauge for the metric, but also for this higher spin tails. Then I want to think about this as this Timelike Toda emerging as this gauge fixed version of this 2D higher spin theory. And so now I have this meta theory that depends only on the background values of this higher spin fields, and I have some ghosts because I went to a gauge. So these ghosts now are generalizations of the BC ghosts for which have the central charge -26, but here I'm gauge fixing higher spin fields, so I need more. And this is this ghost part here. And this Toda part here is the action that you've seen in the previous slide. And I will hopefully be able to motivate in the next slides why this thing over here makes sense. So, and for each n, we will still impose the vanishing conformal anomaly. And as I said, C ghost is the ghost partition function. And the central charge for this ghost theories is known. It's given by this following expression over here. For n equal to 2, it's nothing else than the BC ghosts. For n equal to 3, this is -100. For n equal to 3, it's -246. So the central charges for these ghosts, generalizations of BC ghosts, are known. Very good. So this theory, putting it on a sphere topology, makes sense. So I can put it on a sphere topology. I can look at the equations of motion, and I find a saddle. And my saddle is given by the following values of the fields phi. So I have my phi1, which is this one field that's actually very special in this Lagrangian here. So the phi1 is the one field that's popping up in the linear term, and it's the one field that I can strip out of all the exponentials. So phi1 takes a very special role in here. So phi1 takes this constant value, and all the other phi i's are 0. So I have to saddle with these values of the phi's. And indeed, as I was saying, so I want to interpret the phi1 as the Weyl factor. And I want to interpret the phi1 as the Val factor because it obeys the following symmetry transformation under Möbius transformations. So under Möbius transformations, f phi1 transforms in the following way, which is exactly how the Val factor transforms in Timelike Liouville theory, whereas all the other phi's transforming this way. And if I now evaluate my Timelike Toda path integral to leading order, for large C matter in the saddle point approximation, I find this expression over here. There are some very interesting pieces in this expression, I think, for example, like the C matter over 3, which looks a little bit like some entanglement entropy, maybe not. And then there's some other corrections. But let me go and search for fluctuations. Good, because this is where I wanted to get. So this is where we were before. This is where we were when we looked at Timelike Liouville theory. Now we study Timelike Toda on the sphere topology, fluctuations around the saddle. And we find not just 2, but we find 6, 12, 20, and so on and so forth. So we find all these like masses, m squared, all these tachyonic masses. And moreover, what you can see here is that for this equation over here tells you that it's 0 for L equal to 1. This is 0 for L is equal to 2. This is 0 for L equal to 3. So this theory has n squared minus 1 zero modes on the sphere. And this is why I think this theory on the sphere makes sense, because I divided by PSLN C, and PSLN C has n squared minus 1 non-compact directions, so I can use my zero modes to kill this infinite volume and make it, at least for finite n, make this volume a finite n group. So I already succeeded compared to like higher spin theories, because my infinite higher spin group in 4 dimensions, in 2 dimensions, at least for finite n, I can make it a finite dimensional higher spin group. So I will not discuss the phase, but it's there. And indeed, for each component, if you properly evaluate this one loop contribution, you find the following expression, and you find the Harry-Steinberg character for the discrete series representation. So with conformal dimension delta, that's now not just 2, but 3, 4, 5 to n. And the phi1, which is the one phi that I interpreted as the Val factor, has conformal dimension 2. So it's really the gravitational subsector of this theory. And and then we have this edge part, which comes again because I have a bunch of zero modes that I need to strip off if I do this one loop, this heat kernel analysis. Maybe one thing that I hadn't said before is that this factor of 2 here is because I have a discrete, in the discrete series, I have a highest rate and a lowest rate representation, and so the 2 accounts for both of them. Very good. And now, I know how I'm doing with time. We're doing good with time.
You have a few minutes.
Okay, good. So, perfect. So, this didn't make any sounds. So, okay. So, very good. So, of course, I mean, in Toda, I didn't have only the character of one delta, but I had the character for like the discrete series character for delta equal to 2, 3, 4, 5, and so on and so forth. So what I need to do if I want to calculate the full 2D higher spin theory, I need to take all my characters and sum all my characters. Now remember that this was not possible in 5 dimensions, 6 dimensions, and anywhere else. In 3 dimensions, there is nothing that's fluctuating. So, but in 2 dimensions, we can, much in the spirit as like the 4D theory, we can sum these characters. So we can sum all these higher spin characters. So I can perform this sum. And of course, here I don't only have Toda, but I have also the ghosts and the matter. Fortunately enough, I can also sum the ghosts. So I can also get my one loop contributions for these like higher spin ghosts. And here I can use a very neat trick. I can go back to like ADS here actually for one slide and use double trace transformations to get these ghost characters. Because if you want to calculate this ghost contribution, you need to do a heat kernel of a Green's function. And for that, you use the double trace transformations. But point being, I also have the one loop contribution of these ghosts here. So I can also sum them up. So much in the spirit like the 4D theory, I can build a 2D theory with discrete series representations, and I can sum all these characters. So I can start looking for a boundary dual. But maybe because it's lower dimensions, maybe it's easier to track down what is this boundary dual theory. So, and this is really where I want to go. And I'm using my last 1 minute or 2 minutes to mention a few more things. So for finite n, also like this theory, also like the one thing that maybe I haven't stressed enough. This is a theory, this is a 2D dimensional higher spin theory, and that has a Lagrangian. So compared to 4D, I have a Lagrangian. So I can like really like also like at least for finite n, I can like calculate my melodic diagrams up and down. But still, if I send n to infinity, which I can because then I can still sum all my characters, then this 2D Toda theory becomes a 2D higher spin theory. But compared to 4D higher spin, I have this Lagrangian, which gives me access to higher loops. And I have this extra parameter n that counts the number of higher spin fields. So maybe I can play around with it a little bit more. And for finite n, we could gauge this higher spin group down to a compact group. So this gives us maybe a bit more wiggle room to like see, okay, how are we dealing with this infinite higher spin group? But similarly to the 4D theory, I think we had all this discrete series representation. So we had still found all these gauge fields. And the Harshana characters were summable. And okay, we had the conformal mode problem. So this theory really captures like a lot of data from the 4D theory. And so I think my take for right now is that I want to analyze this characters more. And the hope is that there is some dual theory. I mean, if it exists, it has to be incredibly simple because what we have like an infinite number of symmetries in this 2D bulk theory. So whatever is on the boundary, if there's something at the boundary, it has to be very simple. So there's some insights and some ideas that maybe this is somehow related to the Q equal to 2 SYK model because at low temperatures, the conformal dimension of the fermion is like delta Q is equal to 1 over Q. And so if you take Q equal to 2, then it's a half, and the half plus a half is 1. So you can build composite operators, then they give you like this integer conformal dimensions. You can also study the ADS counterpart, so put this more like Toda theory on the Poincare disk. Then you don't run into trouble of zero modes, and actually this is incredibly nice. It can be summed up, and it's very sweet and nice. I started out still discussing this Lorentzian higher spin wave function. So I mean, I think it would be very natural also to just like study like the wave function, this Timelike Toda theory, or what are the Wheeler-DeWitt equation of this theory. And I mean, there are infinitely many symmetries. So how do we get about this? And there's many more things, but for the sake of time, let me stop here and thank you so much.
Does the spectrum of the Toda theory exhibit a gap between low scaling dimensions and high scaling dimensions?
No, they're all like, no.
So would you expect that the bulk would be stringy in this case?
I don't know. It's an interesting point. I don't know.
Does a space like Toda theory have a matrix model description?
Not as far as I know. And the space like Toda has this T relation like this. Yeah, no, not as far as I know.
Why is it important for you to have a conformal mode problem for the Toda theory? In the context of the n equals 4 superunions, I think that there is no conformal mode problem there.
But I want to mention, if in the end, like all my, if my discussion is going back and forth to 4D. So if I want to send like 4D Euclidean path integrals, and 4D de Sitter on the sphere has a conformal mode problem. So it's good to have, I mean, if you evade it in 2D completely, like how can you learn something about 4D?
Can you comment more on the large n limit? Is there any simplification happening?
There are simplifications of the characters. I wrote them down, but I don't have any interpretation for them yet. But these characters, like they sum up very nicely. So I mean, I think this is for ADS. So in the ADS case, they sum up like, so you have all these fields that sum up, and they give you only this, and like sorry. Oh, this is the Sitter case. So I take a W1 plus infinity here. This means that I added something with conformal dimension 1. And then I take all these characters here, and they were a little nasty. But if you sum them all up, they just give you these two characters. So it sums up to something very nice. So I just need to, I don't know, interpret it like better. But yeah, but you see, like, I mean, in 4D, so I mean, this is like the just to maybe stress this a little more. So I mean, in the ADS, let me do the Sitter case. So if in the 4D theory you sum up all these 4D higher spin particles, then what you end up with are these two expressions. So you had all these higher spin particles, summed up all the characters of these higher spin fields, and what you end up with like two characters. And this first is a character of a conformal higher spin field in DS3, and this is the character of a conformally coupled scalar in DS3. So this tells you a lot about what the 3D theory can be. I mean, it needs to somehow capture like this things. So I mean, it's similar to like the ADS case, where this is really the result of like this work of Jambi, Klebanov, Yin, and so on and so forth. So if you do the calculation in ADS, where we know that this theory is dual to this like ON vector model, so you sum up all these higher spin fields in the ADS side, in the bulk side, and you find this expression over here. And it's again just a conformally coupled scalar on the 3 sphere. And so it tells you, it gives you a lot of data points of what you need to look for on the boundary side. So and you know, yeah. Okay, I hope this was not confusing, but hopefully helpful.
Your formula for the partition function of Liouville theory, is that the analytic continuation of the
This one?
Is that the analytic continuation of the space-like one?
Yes.
So is it understood why only two saddles contribute and not the infinite saddle?
To some extent, yes. To some extent, no. I'm also looking at this a little bit closer with one student, but let me go back to this. Sorry. I think, and I mean, Daniel and Edward are here. So I mean, I think this is for this two saddles, and the appearance of these two saddles. I think it has to do with the fact that if you do like the path integral, then whether you integrate the 0 mode first and all the other modes last, or the other way around. But I think roughly the way that people look at it, and I want to understand better, is that somehow this is related to like the integration contour of the gamma function. So if you do the integration contour of the gamma function or the integration contour of the inverse gamma function, so then Timelike Liouville theory is in spirit the same as integrating the inverse gamma function. And for that you also just take two saddles. So it's really like the contour that you need to take to this integral. It's related to the contour basically. But it's so because there's only two saddles. Because in Spacetime Liouville theory, it would be infinitely many saddles.
But your bottom formula is for the space-like Liouville, right? And then you continue, or is that the formula for time?
No, it is for the Spacetime Liouville theory, but it's continued. And once you continue, then if you said B to I beta, then this becomes some of the signs here change, and then the sign from downstairs goes upstairs. And so that's why here you have like only two saddles.
Okay. Let's thank Beatrix again.